Hello everyone, this is Professor Iris Miano at SMC with your 2 plus 2C, Math 2 plus 2C that is, video on various factoring strategies. So one thing we'll need to get very good at before we even start this discussion is finding the greatest common factor numerically. Okay, so I have several examples that I wanted to go through to show you a strategy in order to do that, and it involves a factor tree. So if you've ever seen a factor tree before, you pretty much know what this is. You'll use a factor tree to if you're going to follow this process, that is, to find the prime factorization of a number. And then you'll identify all the common primes that occur over all of the factorizations that you've completed. And then the product of the common primes is going to be the GCF, or greatest common factor, of all of the integers being considered. Okay, so let's start off relatively simple and just try and find the GCF of two numbers, 45 and 75. So the first thing that we'll want to do is draw up the factor tree. So as I click through here, you're going to see this factor tree being populated. So how do you make a factor tree? Well, here's one way of making a factor tree for 45. It's not the only way. You just need to split off two branches that multiply to give you that original base number, right? And then if one of the numbers in the split is prime, you'll circle it, and if the other one is composite, then you'll continue to split it as so. Same thing was done for 75, and then you'll get your prime factorization among the prime fruits that that's the way I like to describe that. Here is an expanded version of the prime factorization of each of these factor trees, okay? So then you're going to find all of the common numbers like that you see among them. So I have one of the threes boxed here and the only three on the 75 factorization boxed here. And why am I not boxing this 3 over here? Well, because you have to box the same number of the common factors that you see among them, the highest number that's possible. Yes, there's 2 over here, but there's only 1 here. So among the 2 factorizations, they have one single factor of 3 in common. So hopefully that makes sense for everybody. Similarly for the 5, yeah, they have a factor of 5 in common. This factorization over here has 2 of them, but among the 2, if you're considering them both, like how many do they both have in common? Well, just the one single factor of 5, right? Okay, cool. So then you take the common factors that they have, whatever's boxed up, and you multiply them all together and you get your GCF, which in this case will be 15, okay? Let's go ahead and try another example with numbers 32 and 33. We're still going to go relatively simple with it and just find the GCF of 2 numbers. Again, the process starts off the same. Do your prime factorization, your factor tree. Okay, so 32 is what, 2 to the 5th power, okay? Maybe you already knew that right off the bat, but here's a factor tree mechanism by which you could determine that. And I showed the expanded way of writing the factorization. I don't use exponential notation specifically because I want to look at the explicit number of each individual factor. So look at these prime factorizations. Do you see anything in common with them? Well, no, there are no common factors here. So in that case, the GCF is going to be just 1, okay? If there are no common factors, that doesn't mean that a collection of numbers does not have a GCF, a greatest common factor. It just means it's the generic factor that all numbers have, and that would be the number 1, okay? Cool, let's try 3 numbers now, 14, 24, and 60. So go ahead and factor tree them. Here we go. Okay, all done. Write their prime factorizations expanded. Remember to avoid exponent notation there. And then ask yourselves, okay, what factors are we dealing with among all these factorizations? Well, there's 2s, there's 3s, at least in 2 of them, and there's a 7 and there's a 5. Okay, so let's start with the 2s because they all have at least one factor of 2, right? So go ahead and box that single factor of 2 that they all share. Okay, and then ask yourself, is there a second factor of 2 that they all have? Well, these 2 numbers have a factor of 2, but this one doesn't. So the 2s are done, right? Do they share any other factors besides one factor of 2? Nope, that's it. So therefore, the GCF is 2 among the numbers 14, 24, and 60. Okay? You guys feel me on this? I hope. Let me know in class if you need a little bit more discussion on this. Okay, so now let's switch gears over to something a little bit more challenging and find the GCF of a list of terms. When variables are involved, right, it's going to be, you're going to have to incorporate some investigation involving the variables. And how do you determine? Well, it's going to be the lowest exponent present for each distinct variable. Okay, so here are two examples. We've got lists of terms, and one way you could do it, at least to start the process, is just to expand out each of the individual exponential expressions, right? Like go ahead and write y to the fourth as 4 factors of y, y to the fifth is 5 factors of y to the eighth is 8 factors of y. And it's nice if you can line them up like this, like I've done so far here. So you can look, well, how many factors of y does each of these individual terms have? Well, they each have 4, right? This this exponential expression has another one, right? But it's no longer matching up with the first expanded version of the exponential expression. Okay, so it's like and the rule of thumb, the shortcut is just to say, well, which one, where's the lowest exponent for that particular variable? All right, now for e, we can again, here we go. This is me presenting, yes, the GCF is y to the fourth. Okay, now for e, we expand all these two terms here, and it's probably pretty obvious that among the two factorizations or expansions, they just have one factor of x in common, so therefore the GCF is just an x. Okay, now throw coefficients into the mix and it can get a little bit more wild, but you know, the process is still relatively similar. So you could do separate work in order to find the GCF of the numerical parts of each term, and then separately consider the variable part as well, and use those two different methods. So if you're just thinking about the numerical part, you could do the whole prime factorization factor tree thing and go through the whole process, or you might be able to recognize, because the numerical values of -9, 15, and 6 are relatively small, you might be able to pick apart those factors just kind of in your mind, do a little bit of mental math. But by all means, if writing it down is helpful, definitely do that. Do not ever shy away from writing down steps in order to complete your work. Ain't no shame in that game. All right, but anyway, you might have noticed that the GCF for the numerical parts of the coefficients is 3. And why is it 3 and not -3? Like, does this negative sign come into play? It does not. Until you get into factoring polynomials, that's when the signage can play a factor into a factorization, and I'll show you when it's relevant for that. Unless, of course, all of these 3 terms in the list were negative, then you, of course, that negativity, that factor of -1 would be common among all 3 of them, and then the GCF would be negative in that case. But just having one of them, it's not enough. Okay, now the GCF, therefore, of the variables would be the x, because that is the lowest exponent that you see among all of the variable parts of these terms. Okay, so slap them together, and the collective GCF of these 3 terms is the numerical GCF of the coefficients and the GCF of the variables multiplied together. Okay, let's do this another time with this next example, g. Okay, so tell me, what's the GCF of the numerical parts? Well, it looks like it's going to be just 1, because the coefficients being 11, 1, and 1 respectively, while they only share the most generic coefficient of all, or factor of all, and that's just the 1. Now, what would be the variable GCF? It looks like they have at least 1 factor of A and at least 2 factors of B, so I would call that AB squared. So therefore the GCF would be 1 times AB squared, or just AB squared. Cool. Moving on. Now let's factor out a GCF out of a polynomial. Okay, so you'll want to find the GCF, the numerical GCF and the variable GCF if it exists, and isolate it, and then pull it out to the front and write down the remaining factors in a set of parentheses. So here we go. Let's first tackle 49x minus 35. Okay, we've correctly determined, perhaps through some processes, maybe you pressed pause ahead of time. Sorry, I didn't give you any warning, but the GCF is 7, okay, for the terms 49x and the subtracted off 35. And so you can rewrite this binomial with the GCF factor isolated. And I've also lit it up in red just to make it really pop. And then you can factor it out, which means just pull that common factor out in front, and the 7x and the subtracted off 5 are going to be left inside of a set of parentheses in order to write the or present the factored form there. And that's it. There's all there is to it. So that's going to be your final answer for example H. Now for I, we need to determine the GCF for z cubed minus z squared. Okay, so there's no real interesting numerical GCF. It's just a 1, but it looks like they both have at least 2 factors of z in common. So z squared therefore will be the GCF. Rewrite this binomial with that GCF isolated, and then of course write whatever leftover factors are there as well. And don't overlook the fact that z squared, when you isolate z squared from itself, you want to have some sort of appropriate placeholder factor there in order to correctly determine in the next step when you factor, like what's going to be left behind. In this case, it's the 1. So whenever your GCF is the entirety of a term, make sure you leave a 1 behind when you do the pull out that common factor. Okay? Cool. All right, let's get into some more, complicated examples. Now, for J here, this trinomial, there's going to be a kind of counterintuitive rule of thumb that I want to teach you, and it's this. When your polynomial or a grouping associated with a polynomial has a leading term that's negative, then the GCF becomes negative, okay? I know that might sound a little weird, and also considering that among the 3 terms, only 2 of them are negative, this one is not. It's just going to make your life easier, especially when you get into factor by grouping, which is coming up later in this video, okay? So considering that, let's see, what will the GCF be for J? Maybe pause the video here if you want to calculate it off to the side, or just take a little bit of a think about it. Okay, so if you've done that, you'll get that negative 2b is the GCF. And yes, I have a little note here reminding me that this is since the leading term is negative. Okay, so isolate that particular factor in each term, and then I use a raised dot here to still combine it multiplicatively with the remaining factors in each term. And remember, that last term is the entirety of the GCF, so make sure you're leaving behind a factor of 1, and then pull out that common factor of negative 2b, leaving the 6b squared, the subtracted off 5b, and the added 1 inside of the set of parentheses. And then you're set. All right, cool. So hopefully this is getting easier as we go. Let's look at example K. Numerically, it looks like the GCF is a 9. They all have at least a factor of 9. They all at least have 1 factor of x, and they all at least have 3 factors, it looks like, of y. So I believe 9xy cubed is the GCF. Isolate those factors within each term, and then pull it out to the front and write the remaining factors as the terms inside of the parentheses. And that's all there is to it. Okay. Moving on, let's see. I got a few more factors now, or examples. Now, for example L here, we have, technically this is a binomial, okay? And each term in the binomial has in itself a binomial factor. Wow, it's very meta here, okay? So considering the other factors that are involved in the 2 terms, the 13 and the x, it looks to me like the GCF is going to be that binomial factor of the quantity y minus 1. So go ahead and isolate it, pull it out to the front, and the remaining quantity will contain the leftover terms of x minus 13 here. Okay, cool. Now in example M here, again, we have a binomial with a common binomial factor. It is the GCF, and so we'll pull it, we'll isolate it, we'll pull it out to the front and write the remaining stuff in black in its own set of parentheses, and you have factored that polynomial in example M. All right, cool. Moving on. Ooh, let's have some examples and demonstrate how to factor by grouping. Now, depending on your background, you may have seen this before, so hopefully it's a little bit familiar, but if it's not, it's all color coded, and hopefully it's going to be kind of a fun process for you here. So the procedure, let's go over what we expect to do as far as the steps are concerned. Step one, we're going to group terms into two groups of two terms so that each group has a common factor. So this might involve rearranging some terms, which is fine to do as long as you have, if a term is being subtracted off, that negative sign out in front needs to come along for the ride. We're going to factor out the GCF from each individual group. So there's going to be two possibly distinct GCFs happening. If there is now a common binomial factor in the groups, you want to factor that out. If not, rearrange the terms and try this process again. So, it might not work out the first time, in which case, if the polynomial is indeed factorable, you should be able to rearrange the terms and figure it out, giving it a second go or third go, depending on how you rearrange things. Okay, great. Let's try some examples here. Here's example N. I'm going to go ahead and leave the the terms in the order that they are given to me and group them accordingly. So notice that I have boxed up my groupings and I put a plus sign in between, okay? So it's like I haven't really changed the polynomial. I have just done a little bit of cosmetic, adjustment there just to aid in the process. So we're going to first find the GCF of this grouping, which I believe is A, and then the GCF of the second grouping, we'll find that, and I believe that will be 7. So for the individual groupings, go ahead and isolate their GCFs of A, which I've isolated in green, and 7 that I've isolated in blue. Pull them out in front of their individual groupings, and notice that the binomial factors that are left behind are the same. They match. So now we're going to isolate them and pull them out to the front, leaving behind the remaining factors among the two terms of A plus 7. Okay? Cool. Great. That's that. Let's go ahead and do this again for example O, and it looks like we have common factors among the groupings in the order that they're presented. Usually when you do this process, you just kind of try it out and keeping the terms in the order that they've been given to you. As long as there is some GCF, it should be fine. Now look at this first grouping. It looks like the GCF is going to be 7x squared. So the entirety of this term. So remember to leave a factor of 1 behind. And then for the second grouping, it looks like the GCF is going to be a 3. So go ahead and isolate those GCFs and factor. And then recognize, this is working out so beautifully, we have common binomial factor of 4x minus 1. Go ahead and pull those out to the front of each of the terms, factor it out, and then report the remaining terms in their own quantity here. And that's that. That's factoring by grouping. I have a few more examples I want to go through with you, so just bear with me here. Let's tackle example P. Go ahead and leave the terms in the order they've been given to you, and recognize, though, that I've done something special in the rewriting, okay? Notice that the first term in the second grouping, which is also the third term in the original polynomial, notice that it is negative. The term is negative, it's being subtracted off. So conventionally, when you do this boxing up, you will want to absorb that subtraction symbol as a negative sign of the first term in that grouping, and then add a plus sign in between the two groupings. Okay, that might not be intuitive, but it's conventional. It's a thing that's going to help you out definitely in this process. So make sure that you are getting into the habit of doing that. All right, GCF of the first grouping is going to be y, I believe, just one factor of y. Okay, and then the GCF of the second grouping, well, the first term is negative. Both terms happen to be negative. So regardless, though, if as long as this first term is negative in this second grouping, your GCF is going to be negative, and I believe it's going to be negative 2. Okay, so isolate those GCFs of y and negative 2. Pull them out in front, and awesomely, we have a matching binomial factor of 2x plus 5y. Pull that out in front. go ahead and write the remaining items inside of some groupings. And whenever you have the remaining items do something like this, where it becomes technically a y plus -2, whenever you add a negative number, it's equivalent and more concise and aesthetically pleasing to rewrite it as subtraction. You know, there's just fewer operations going on. It's just more to the point, and it's conventional, all of those things. So we want to get into the habit of that in writing our final answer. So here, what you see in all black is our final answer associated with that factorization. Okay, example Q. We're going to keep our groupings. Or no, sorry, I went ahead and did a little switcheroo here. Okay, yes, look at that. I forgot that I did that when I wrote this. But yeah, I noticed that the first two terms have a GCF of 1, and the second set of two terms also have a GCF of 1. So I went ahead and did a switcheroo on the middle two terms so that they would have more interesting GCFs. And so let's go ahead and figure out those groupings, right? And again, because the third term of the polynomial, as I've rewritten it, becomes the first term in the second grouping, I make sure that I have that subtraction symbol turn into a negative sign and add the two groupings together outside of the boxes. The GCF of the first grouping appears to be x. The GCF of the second grouping appears to be -4. Let's go ahead and isolate those GCFs, pull them out. Awesomely. Oh, wait. Do I have common binomial factor? Is 3y plus 1 equivalent to 1 plus 3y? Yes, it is, because addition is commutative. So I went ahead and did a switcheroo on the second binomial here where my cursor is hovering, okay, just to make it look exactly the same. Now I feel confident about isolating the now explicitly common binomial factor of 3y plus 1, pull it out to the front. We have x plus -4 in the other binomial, call it x minus 4, and then you're done. So in these examples, I hope I'm able to show you some of these weird caveats that you might have to consider in your factoring by grouping endeavor. All right, let's do another one here, example R, and let's do a grouping that makes sense. Probably just the way that it's given, it looks good. Okay, the GCF of the first grouping appears to be 2, the GCF of the second grouping appears to be x squared. Isolate those items, factor them out, and oh goodness, look at this. This hasn't happened before. Our binomial factors do not match. Okay, so this isn't working out, but if you remember the process, we should rearrange the terms of the original polynomial here and see, try the process again and see if we can get it to factor. Now, I'll let you press pause maybe if you want and see if a rearrangement is going to work out. All right, if you're back, did it work out? No? Well, that's because this polynomial can't be factored by grouping anyway. So that will happen from time to time. So, you know, don't sweat it. Just say it cannot be factored by this method and move on with your day. Okay? All right, let's do this last example in this PowerPoint. And then I also want to do some factoring trinomials in the latter half of this same video. I just want to do it all in one go. Okay, but let's factor this bad boy by grouping. Now this one's particularly special, and it involves a first step that I actually haven't had the opportunity to consider because of the nature of all of the previous examples. Do you notice how these four factors, or sorry, these four terms in this polynomial share a common factor, like right from the get-go? Yes, they all share a factor of 5. So let's go ahead and isolate a factor of 5 and pull it out before we start the factor by grouping process. Okay, and what that does is it actually makes the rest of the process a little bit easier because there's a numerical factor that you don't have to consider anymore in regard to figuring out the GCFs of the two groupings. Now go ahead and make your groupings happen. Find the GCF of each grouping. For the first grouping, it appears that the GCF is 3z. The second grouping, it looks like the GCF will be what? -y, if I'm not mistaken. Yep. So let's go ahead and isolate those GCFs for the individual groupings, factor them out. Oh, awesomely, the binomial factor of x minus y appears in both of the terms. Pull that out to the front, factor, and look at what's left. Oh, we have a 3z plus -y. Call that 3z minus y. and you're set. Just along the way, don't forget that you still have this factor of 5 that's just kind of coming along for the ride. That's something that's easy to forget about. So try your best not to do that, okay? Cool. So that's it for GCF and factoring by grouping. Let's also continue our discussion on factoring strategies by factoring some trinomials. We're going to do trinomials whose leading coefficient is 1, quadratic trinomials, and or second degree trinomials, I guess is what I'll say. And then also if the coefficient is not 1. And I like to do the diamond method. Have you guys ever seen the diamond method before? It's pretty cool. It's totally my jam. I like it better than trial and error, although you're going to have a handout about trial and error. And you're going to find that it's not a super fun method, but you're going to have to go through some pain first of trying it before you recognize that it's just kind of a thumbs down method. Okay, let's go ahead and practice the diamond method though, with the leading coefficient being a 1. So your polynomial will have the form x squared plus bx plus c. Your a, as it's quintessentially fitted or affixed as the coefficient of the leading term, it's going to be a 1. So it's just kind of invisible there. All right, here's your diamond. The first thing you're going to do is put the c, or the constant term, in the top of the diamond. Then you're going to put b, the coefficient of the middle term, on the bottom of the diamond. You want to find two numbers who simultaneously sum to the bottom diamond number and multiply to the top diamond, right? So it's got a sum to b but multiply to give you c. Put those numbers in the remaining diamonds, and I just generically put them as these symbols here, and then you could go straight to the factored form in order to complete your factorization endeavor. Okay, now if the a value, the coefficient of the leading term for your second degree trinomial, is something other than 1, then there's more process after, like step 5 continues into step 6 and so on and so forth. But the first 4 steps are going to be exactly, or are going to be very similar. Actually, step 2 is going to be a little different, but we'll get to that. We'll cross that bridge when we get there, okay? So this is the method if your leading coefficient is 1. So let's have some examples here, okay? Great. Let's factor completely part A. We're going to have, let's see, so what do? We put the 20 on top and the 9 down below. So you have to come up with two numbers that simultaneously add to 9 but multiply to 20. So I believe 4 and 5 are going to do the trick. And then you can go ahead and write the factored form straight away from there as x plus whatever this number is, x plus whatever that number is. And there's plus signs here separating these these terms because the numbers that finish the diamond were positive, okay? And that is a consequence of the initial numbers, the 20 and the 9, the C and the B respectively, both being positive terms, okay? But now, for example B, we're going to have a negative value in the mix. So let's see how that changes the conversation. So go ahead and initialize your diamond by putting the constant term of 33 up top, the negative 14, make sure the sign comes along for the ride, down below in the bottom diamond. So now our task is to find two numbers which simultaneously multiply to give a positive 33, but add to give a negative 14. So since it needs to add to be a negative number, either one of the numbers in here is going to be negative or both of them. But hold on, consider this. If the two numbers have to multiply to give you a positive number, then that should tell you that these two numbers that finish your diamond both have to be negative, because that's the only way you're going to multiply to get a positive, having at least one of them be negative so that the sum is negative, okay? There's a lot happening here. But it looks like negative 3 and negative 11 will fit the bill, right? They'll multiply for a positive 33 and they'll add to a negative 14. So go ahead and write the factored form as x minus 11 times x minus 3 for example B. Okay, moving on. More examples. Let's go ahead and initialize our diamond. We have a negative product but a positive sum. So that means that one of these two factors that finishes the diamond is negative. And since the sum is positive, the larger of the two factors has to be positive. You see what I mean? That's the only way this is going to work out. So think about factors of 36. leave the negativity out of it for a moment. And when you go through all of the possible factorizations, I believe 4 and 9 are the most interesting ones because they have a difference of 5, don't they? Okay, so as long as the 9 is positive and the 4 is negative, this combination of numbers is going to finish our diamond, because check it out. Negative 4 times 9, that multiplies to a negative 36, and then they also add to a positive 5. So there you go. There's the factorization there. Okay, moving on to example D. Initialize the diamond. Negative 40 needs to be the product. Negative 3 needs to be the sum. So again, we need one factor in the 2 remaining diamond spots to be negative, one's positive, and the larger of the 2 is going to need to be negative so that the sum is going to end up being negative. So let's think. 40, huh? That's 2 and 20. No, that doesn't have a difference of 3. There's 8 and 5. Oh, 8 and 5, I think will do it. They have a difference of 3, don't they? So let the 8 be negative, the 5 be positive, and then write the factored form straight away. Great. Moving on. Oh, lots of examples here, guys. Let's factor completely. Example E. All right. It looks like we have 15 up top, 6 down below. Okay, so factors that multiply to give you 15, and it's positive, so we know both of the remaining factors are going to need to be positive. Let's see, it'll be 3 and 5 are the only ways you can multiply 15, other than 15 and 1, but that doesn't have a sum of 6. 3 and 5 don't have a sum of 6 either. You might be stuck. Yeah, so this turns out it's actually not factorable. So we would say that this trinomial, second degree trinomial, is called prime. Okay, that's the key word you can use, and that just means it's not factorable by this method anyway. Okay, now we can move on to F, which is a particularly challenging example because there's more than one variable. So what you do here is there's a little bit of a trick. Let's let A be acting like the variable, and B will just be act like a numerical factor. So in that case, you're going to initialize your diamond upper and lower areas accordingly, where you take the entirety of the constant term 30b squared and you put in the top diamond, and the bottom diamond you do the negative 13b, everything except for the a value, which is acting as the variable. So therefore, if b is acting more like a number, it's going to be part of the coefficient, so to speak. All right, so we got to find two numbers that multiply to give us 30b squared and add to negative 13b. Okay, if it's a negative sum but a positive product, both have to be negative, and they both have to contain a factor of b, right? Because that's the only way they're going to be able to be added, and also multiply for a second degree term in b. So it looks like it'll be negative 3b, negative 10b. There you go. And then go ahead and write the factored form accordingly, with a acting as the variable this time. Okay? Cool. Now let's go ahead and do some other examples that what's the word I'm looking for, are quadratic in form, but just look a little strange. Okay, and before we get too deep into this, hold on, I need to just do something really quickly, just a moment. Okay, and we're back. Thank you so much. Sorry, I had to step away for a moment. But let's get back to our examples of factoring, and now we're factoring second degree, or no, sorry, this is a fourth degree trinomial in example G, but it's quadratic in nature, so we could still treat it like we would factoring a quadratic or a second degree, because it's fourth degree here, or some even numbered degree for the first term, and when the middle term is exactly half of that degree, and then you have a constant term for the first or for the third term, you can still use this method. So you put you just make sure that in these positions here you have x squareds rather than just x's. It's just whatever is in this position goes here as well in the factored form. So go ahead and put your 21 up top, your 10 down below. Ask yourself, what numbers can multiply to give me a positive 21 but simultaneously add to give me a positive 10? That'll be 3 and 7. Go ahead and add those to your already pre-established factored form there, and that's it, and then you're good. And if you are wondering, oh, did that really work? Do I want to, verify this? You can always FOIL this back out, and you're going to get this original fourth degree trinomial back again. Okay, let's look now at this example in H, and just recognize that, oh, we have a quadratic trinomial or second degree trinomial. It's just the terms are in a weird order. Just go ahead and reorder them. That's fine. Just, put them in descending degree order, and factor accordingly. So the method still is, in this case, the 30 up top, the negative 31 down below. Well, if we're trying to sum to a negative number but multiply to a positive, both of the values in the remaining diamond spaces need to be negative, and negative 30 and negative 1 will do the trick. Go ahead and go straight to the factored form there. Okay. So when the terms have a common factor, we'll of course factor the GCF first, then perform the diamond method. So here's a few examples of which that would be relevant. For example I, notice that there's a GCF of x. Let's pull that out first. Now the remaining second degree trinomial that's in the quantity, go ahead and diamond method that. Negative 4 up top, 3 down below. The remaining values will be negative 1, positive 4, and you could reverse the order here, doesn't matter. And then go to the factored form for the second degree trinomial bit. But don't forget that the x is still coming along for the ride, okay? Similarly, but more complex, in example J, we have a GCF of, it looks like 5x to the third power. Yep, so I'll pull that out. And the remaining trinomial is the second degree, so we can diamond method it up. Here's how we'll finish that and write the second degree trinomial in factored form there. Don't forget about your 5x to the third power. It's still very much involved in the factored form that you need to present for your final answer. Okay, now let's do the diamond method when a does not equal 1. So we have a non-trivial leading coefficient. That's this value right here. Okay, something other than 1. What do? Well, we still can use the diamond method, but there's going to be a subsequent a series of steps that are associated with factoring by grouping. Okay, so here we go. And also this second step is slightly different than the previous method where a equals 1. So since we have something non-trivial in this position right here, it's actually the product of a times c that goes in the upper diamond. The lower diamond is still populated with the value of b, the coefficient of the middle term, and then you still find two values that multiply to give you this top value, a times c, but simultaneously add to give you the value down below in b. So generically I put these symbols in here, and then you're going to use them to not write directly the factored form. You're not done here. When the a value is negative 1, you have still more work to do. You need to use these two coefficients to do what I like to call splitting the middle term, okay? That bx is equal to box x plus circle target x, okay? It's you're just splitting the middle term into two separate terms according to what values finish your diamond. Then you factor by grouping after that. Okay, cool. So the factor by grouping will be specific to whatever the numbers are. Let's go ahead and entertain some specific examples here. Okay, example A here. Now, this first part of the process, remember the top diamond is not just C anymore, it's A times C, and the bottom number is going to be your B. So you'll have 20 up top, 12 down below. What two numbers will multiply to give you 20 and add to give you 12? Well, 10 and 2 will do it, or 2 and 10 as I have it written here from left to right. And then go ahead and use the 2 and the 10 to split the middle term. So you've got to rewrite this polynomial with the split middle term of 2x and 10x. And I went ahead and also in this next step boxing up my pairs of terms so that I can immediately start the process of factoring by grouping. What's the GCF of the first grouping? Looks like it'll be 2x. The GCF of the second grouping, I think it's going to be 5. So go ahead and separate out those terms, right? Recognize that awesomely you have a common binomial factor of 2x plus 1. Pull that out to the front, write the remaining terms in a separate quantity, and you have factored your second degree trinomial with a non-trivial leading coefficient. Let's do it again for example B. So remember up top, you're going to go A times C, so that'll be 6, -5 down below. What numbers complete your diamond here? That'll be -2 and -3, okay? So that one can kind of be a little tricky, but this will do it. So go ahead and split the middle term and start the process of factoring by grouping. The GCF of the first grouping will be 2x. The GCF of the second grouping will be, it looks like -3. Now it's a little tricky here because the second term is not negative. So when you pull out, or sorry, I misspoke. The GCF of the second grouping is not -3. It's -1, okay? And yes, that might look a little bit weird because you're like, oh, it looks like the GCF is 1. They don't share any common factors, but look, the leading term in your second grouping is negative. So therefore, your GCF has to be negative. That's just a rule of thumb associated with this process. And yes, it is very counterintuitive. So if you're going through this and you're just like, I wouldn't have thought to do that, that's why I'm showing you this example. So we're taking out our factor of -1, and that changes the sign and operation of these two terms inside the original boxing. So that's why when you pull out the -1 GCF, you get positive 3x minus 1. Okay, so hopefully that makes sense. But look, in doing that, we have matching binomial factors of 3x minus 1. Awesome. So that's how you get your final factored form of 3x minus 1 times the quantity 2x minus 1, because that's the remaining stuff outside of the shared binomial factor. Okay, moving on. More examples. Okay, top of the diamond is going to be 24, bottom diamond is going to be a -11. What do we do here? Let's see. 4 and 6, 3 and 8. Oh, I think 3 and 8 will work as long as they are both negative. Yes. Okay, so those will be the coefficients of your split middle term, right? So the next step is rewrite this polynomial, but with the middle terms being no longer minus 11x. It'll be minus 8x minus 3x. Go ahead and do your boxings. Notice that third term with this, once you incorporate the split middle term, is subtracted off. So I have boxed it up inside of the second boxing and then added the two boxings together. That's something that was initialized back when we were talking about just the factoring by grouping process. So remember that. You want to continue to do that. The GCF of the first grouping appears to be 2x. The GCF of the second grouping appears to be -3, okay? Because that first term in the second grouping is a negative number. Okay, so pulling out those common factors, we get a common binomial factor of x minus 4. Pull it out in front, and you're left with the second quantity being 2x minus 3, as shown. Okay, all right, example D, we have 35 times -4 gives us the -140 here. 4 is your B value. This one's a little tricky. You might have to think about it for a second. If you'd like, press pause and play around with some numbers to figure out how to finish this diamond. And if you're ready, here it is. It'll be -10, +14. That's how you'll multiply to get a -140, but also add to give you a +4. So split the middle term that way. Factor by grouping. GCF of the first grouping is 5x, I think, and then the second grouping looks like it'll be 2. Yep, and the remaining binomial factors match of 7x minus 2. Pull them out to the front and encapsulate the remaining terms in its own factor of 5x plus 2. Great. All right. Here we go with some more, and these are getting to be a little bit more challenging, but it's something we can't handle. Notice that there is a GCF that we can factor out before we implement the diamond method, and it looks like it'll be 3x. Okay, so let's go ahead and factor out a 3x from this original trinomial. And then inside we are left with the same kind of second degree trinomial that we've been working with so far ever since we started doing examples in which the a is non-trivial or something other than 1. So just with the numbers and terms that are inside of the parentheses, implement the diamond method. So your a, which is 2, and your c, which is -6, multiply them together to get the -12, your b value being 11. And isn't it nice that we did this initial step recognizing that there was a GCF to take out before we started the diamond method, because then we're working with smaller numbers. It's definitely a step you want to take. You could, well, I think it would be really hard to do it without at least taking out this x factor. The numerical GCF removal is definitely having a benefit, and I would argue that taking out the x would be necessary. Anyway, go ahead and finish your diamond. It'll be done with a positive 12 and negative 1, and keep your 3x outside of what's happening here. Let it come along for the ride. And then inside some parentheses, go ahead and factor by grouping. Okay, splitting that middle term of plus 11y into a plus 12y plus negative y or minus y. But with the factor by grouping step, you need to have that subtraction symbol be absorbed as a negative sign and figure out the GCFs of each grouping. Here, I believe it'll be 2y. Here, it'll be negative 1. And awesomely, inside of here, we have a common binomial factor of y plus 6. Pull that out to the front. Capture the 2y minus 1 into its own quantity. Don't forget about the 3x that you pulled out in the first step. All right, and that's it. This is your final answer for example E. Okay? Example F. Ooh, we've got a leading coefficient that's negative. That's a little weird to work with. If you're very uncomfortable with that, feel free to take it out as your initial step. And then you're dealing with a second degree trinomial with a non-leading or non-trivial leading coefficient that's a little bit more familiar to work with, right? Just take it out if you don't like it. That is if you have a leading coefficient that's negative for your second degree trinomial that you're trying to factor. All right, keep your focus inside the parentheses. Initialize your diamond here, complete the diamond, split the middle term, factor by grouping by taking the GCF of each grouping out. The first grouping here, it looks like it has a GCF of x. The second grouping here has a GCF of 4. Find that common binomial factor of 5x minus 1, pull it out to the front and next to the negative 1, and then the other binomial factor will be x plus 4, like so. Okay. Whew. Are there more examples? Yes, there are. Whew, so many examples. This is a long video, guys, but I wanted to make sure that you had a lot of practice with me. All right, let's go for it on example G. It'll be 24 up top, 14 down below. What numbers finish your diamond? That'll be 2 and 12. Split the middle term, find the GCFs, pull out that common binomial factor of 3x plus 2, and x plus 4 is your remaining quantity. Cool. For H is the next letter example that we have here. We have, it looks like 6 times 7 will give you 42 up top, negative 13 down below. Let's see, I want to say, yeah, negative 6, negative 7 will do the trick. Oh, that's beautiful. Look at that. So your GCF of the first grouping here will be 6x. The second grouping will be negative 7. And there you have it. Factored form in no time at all. Okay, let's see. Okay, another couple of examples that are just a little bit weird. Well, they have GCFs that we want to factor out, right? So it looks like for example I, there's a GCF of y we could factor out, and then just inside the parentheses, focus on that and populate your upper and lower diamonds inside your main diamond. Complete it by figuring out what factors multiply to negative 30 but simultaneously add to negative 7. It'll be negative 10, positive 3. Split the middle term. Don't forget that the y is still on the outside there. Factor by grouping. GCF of the first grouping looks like 2x. The second grouping, 1. Okay? But yes, even though it feels like there's no GCF, there's always a GCF of 1. And if that's all you've got, then pull it out. Make sure you have this factor of 1. Okay? And for this particular example or other examples like it, if your GCF is 1, you still want to pull it out for this process, okay? Because once you take out that 3x minus 5 into the front, you want to make sure that there's something left behind. So you represent the other binomial factor that's left as 2x plus 1, not 2x plus nothing or 2x by itself. That would be incorrect, okay? This is what you want for your final answer for example I. All right, for example J, again, we have a GCF to initially pull out, and it looks like it'll be 2y to the third power, if I'm not mistaken. Yep, there we go. And here's the remaining second degree trinomial. Go ahead and Oh, yeah, that's a big number. 6 times negative 21, that gives you negative 126. And then a 5 down here. Oof, goodness. Taking apart that number and finding its prime factorization would be probably pretty advantageous to this process. It's my hint. Go ahead and press the pause on the video if you want to take some time to figure it out for yourself. And if you're ready to go, just go ahead and we'll go forward and we'll say, all right. Excuse me. The numbers that will complete this diamond are negative 9 and positive 14. There they are. Don't forget about your 2y to the third power. We're going to factor by grouping. GCF of the first grouping is 3y. Second grouping is 7. And the 2y minus 3 is a common binomial factor. The leftover bits is the 3y plus 7. Cool. I want to say, okay, there's one more example, I think, and then this is going to be the end of the video. Thank you so much for your attention throughout this process. I know this one's pretty long. Okay, factor completely, it says. Now notice that we have a trivial leading coefficient, so we can just put the 100 on top, the 20 down below, and then what will complete it? Ooh, 10 and 10. I don't think we've ever had the same number in these two middle diamonds before. This is very interesting. Now what we can do is we can factor by grouping, or we can just go straight to the factored form of x plus 10, right? We could actually skip these steps here, technically. Now, we have a squared, right? A binomial squared. So it looks familiar. You may know this rule associated, right, with it's called a perfect square trinomial, okay? If it doesn't look familiar, don't worry about it. You can always, whether you recognize the structure or not, use the diamond method, as you can see, to factor this trinomial here. If it is indeed factorable, you can always use the diamond method. And if it's not factorable, then, well, you know, you can do some other things to it as long as it's an equation. You could go opt for the quadratic formula, but that's a discussion for another time. We've only been dealing with expressions here, not equations. Cool, and that's it for this. Oh no, do I have, oh, I have perfect square trinomials here. Okay, so there are some more examples here, but we're just gonna leave it at this and call it good on this video, I think, right? Is that what we wanna do? Yeah. Yep, I'd say we've had enough practice here. Okay, so I'm going to go ahead and end this video, and let me know if there's any other things that we could talk about in regard to factoring strategies. Thanks so much.